So in the previous meeting, we introduced ourselves to quantitative methods, and we talked about the fact that it entails certain principles and modalities for understanding data. And particularly when we say data, we mean quantitative data because that's what the course entails. And then we said that one of the major mathematical sciences which underpins quantitative methods, right, is statistics. And so we looked at the statistical pipeline and what the various components are. And then we went on to look at the broad divides of statistics, inferential, and then descriptive. And we talked about what they are. We did indicate that descriptive statistics typically comes in when we are summarizing data. Okay, so when we're summarizing data using quantities like central tendencies and dispersions, then we are applying descriptive statistics. However, inferential statistics utilizes the descriptive statistics to be able to draw further conclusions and generalizations and forecasts. So these were the two broad divides that we considered. Then we moved on to looking at types of data. We looked at the quantitative, qualitative, and underneath each one of them, we looked at the various subtypes. Okay, so all in all, the breakdown was along the lines of quantitative, qualitative, and then for quantitative, you have discrete and then continuous. We talked about discrete being essentially countable quantitative data, whereas continuous data refers to quantitative data that are more measurable than countable, right? On the other hand, we looked at nominal versus ordinal data, where one is just a cluster of names or labels, and the other part being names or labels that have a sense of hierarchy or order in them. So at the first phase of the statistical pipeline, we decided that if it comes to collecting data, there's somewhere that we need to go to, right? Which is the population. And we did understand that here, when we talk about a population, we don't mean it in the traditional sense of just human beings living in the country, right? It's broader than that. Okay, so we're looking at units or elements that reside within a particular domain over a given period of time. So in here, it can be animate or inanimate, and I gave several examples to that effect. We talked about finity and infinity of populations. Okay, the fact that a population can either be countable or uncountable. We also agreed that considering the costs and the time implications of always going to the population, there is a need for us to collect a sub-selection of representative units from the broader population. And then that led us to the principle of sampling. So the plan for this evening is to essentially look at sampling methods. All right, exactly how do we perform sampling? So we'll look at two different types, and underneath each one of them, the plan is to do four. All right, so at the end of the meeting, you should be able to understand clearly and write copiously on sampling techniques. Now, what I'll be doing is that there are certain parts that I would just focus on with just this presentation, and there are parts that I would also where I'll switch over to the other side of the screen where I'll be doing some writing if it requires some illustration. Now, a key thing to keep in mind before I begin is I said that because variables are containers for data, the decomposition of data is essentially the same as the decomposition for variables. All right. So the types of data are the same as the types of variables. All right. So I think you remember this breakdown from the previous meeting. So the only difference is when you're explaining the decomposition for variables, the vocabulary will change a bit. All right. Because you know what a variable is and you know what a data is. So you need to explain yourself in the appropriate regard. So essentially this would be the outline for today's meeting, right? We're looking at 8 different types in all. All right. So in general, there are 2 broad sampling methods. So we can sample probabilistically or non-probabilistically. All right. So in other words, we have probabilistic sample or sampling and then non-probabilistic sampling. And underneath probabilistic sampling, we have 4 types that we will be considering. For non-probabilistic sampling, there are 4 types as well that we'll be considering. So we're saying that probability sampling, first of all, when you talk about probability, we mean or we're referring to randomness, okay? The randomness with which some events would occur, all right? So whenever we talk about probability, the key thing that needs to come to mind is uncertainty, right? Nothing is certain in life, all right? If everything were to be certain, we wouldn't have to plan. Please mute. I don't want to mute everyone because you might want to ask a question. So, okay. So because there are uncertainties, we need to study probability, but this will not be a detailed course in probability, right? This is for that will be the preserve of your colleagues in the mathematics and statistics department who are doing pure mathematics and pure statistics. Okay, here because it's there's a course for the business school, we will just appreciate sampling and probability and statistics from a very generic high level perspective, all right, without delving too much into the nuances. Okay, so probability sampling, right? Here, the samples are selected in such a way that each item or each unit in the population has a known non-zero chance of being included in the sample. Whereas non-probability sampling, here we're selecting the samples not based on any known probabilities, and not all items have a chance of being included in the sample. What does this mean? So in general, when we talk about probability, like I said, okay, events happening randomly. And what does something happening randomly means? It means it's happening by chance, right? It's not premeditated. So for probability sampling, we're sampling in such a way that every element or every unit within the population is giving an opportunity to be selected. It doesn't mean that everyone will be selected, but it simply means that there is equity in the chance that we're giving each item in the population to be selected. All right. So, for example, if you have a class of about,
come and eat your food.
I think at this point, you have to mute the entire class. All right. So that if you want to speak, then you would have to show by hand because there are some distractions here and there. All right. So the whole idea of probability sampling is how can we sample in such a way that we obtain eventually a reduced form or a reduced number of elements, while at the same time giving equal opportunity for each member of the bigger population to be selected. And I was making the argument that considering a class of let's say about 500 people in a class, and supposing that I am interested in selecting a sample of 10 students for one reason or the other, maybe for an upcoming conference or some other important engagement, and I need 10 students to come with me. Obviously, if there are 500 people in the class, I cannot possibly select all the 500 people, right? Now, at the same time, depending on how I select the 10 people from the 500 people, you will either refer to me as being very fair in my choosing or being very biased or unfair in my choosing. Okay, so the idea of probability sampling is the idea that we want to obtain a smaller number of representations from the broader population while being fair to all the other parties or all the other elements within the population. In other words, if I have a class of 500 people, which is the population size, and I'm looking for 10 people, right? How can I select 10 people randomly in such a way that the remaining 490 people will feel that I was fair, although they were not selected? All right. So that's the entire idea. So that's what we mean by giving equal likelihood to each member of the population to be selected. All right. Now, when it comes to non-probability sampling or non-probabilistic sampling, this is the opposite. Under non-probability sampling, we don't care too much about equity in providing equal opportunity for every element within the population to be selected. All right. For non-probabilistic sampling, we're interested in just meeting a predefined quota. So once again, I have a class of 500 students. I'm interested in 10. I can decide that once I walk into the lecture hall, the first 10 people that I engage with will be the people that I would select. So you realize that in general, probability sampling in essence is more scientific, whereas non-probabilistic sampling is not as scientific as probabilistic sampling. All right. For probability sampling, we're interested in providing the units within the population an equal chance or an equal representation, possibly. Whereas for non-probability sampling, we're interested in just meeting a defined quota for a sample without recourse to ensuring that every member of the population was given an equal chance. All right. And when we look at the various types underneath these two broad spectrum, you would get the chance to appreciate them in a lot more empirical sense. All right. So these are advantages of sampling. These are things I talked about, right, in class. The fact that it saves time and it saves resources and so on and so forth. All right. So the very first type of sampling that we would look at. So we're coming to study the probabilistic sampling scheme. All right. I said there are two broad classes. So now we're currently on probabilistic sampling or probability samples. So the first point that we want to take note of is what we call simple random sampling. All right, simple random sampling. And typically in academic literature, you would see SRS. All right. All right, so simple random sampling. Now we call this simple random sampling because of course it's the most simplistic version of sampling that you can ever come across. All right. So what does simple random sampling constitute? It entails the following. So here we are every individual or every unit or every element within the population frame is provided an equal chance of being selected. All right. So technically, we'll say that simple random sampling is a type of probabilistic sampling which involves the shuffling of the population followed by successive selections. All right. Simple random sampling refers to the probabilistic sampling method, which entails the shuffling of the population followed by successive selections. So we can do this in two ways. all right, depending on what happens to every unit that we do select. Okay, so before I look at the subtypes of simple random sampling, I want you to imagine that we're trying to make a smaller selection from a bigger population. So when I say shuffling of the population, think of it this way. Perhaps for 500 people in the class, we can put the name of every member of the class. We can write that down on a sheet of paper and then fold it and then put everything in a bowl. Okay. And then we could shake it. Okay. For example, we can give numbers to each member of the class. We have number one, number two, number three, number four, number five, all the way to class member 500. Okay, all the way to the 500th person. And then we would put all these 500 numbers written in sheets of papers, folded, we'll put it in the bowl, and then we shuffle. Okay, we shake it up just to disturb the pattern so that if I am picking, I don't know that, oh, this is candidate number one or candidate number 30. I will be very fair. And in that regard, everybody would have had the chance of being selected. It could have just been anyone. Okay, but it ended up being maybe this 10 that I selected. All right, so that's what we mean by simple random selection, simple random sampling. We, first of all, are shuffling the population followed by successive selections. Now, there are two types of simple random sampling. Okay, so we're looking at probability samples or sampling. The first sampling method under probability sampling is what we call simple random sampling. We've explained what that is. But now I'm looking at the subtypes of simple random sampling. All right. Now, again, back to the illustration. When we perform the sampling, all right, when we shuffle the population and we're making our picks, two things can happen. It's either when we select a unit, we return the unit back to the population or we isolate the unit. All right. So there could be instances where we shuffle. Okay. We shake the ball of 500 people. We select person number one. I select the first pick. I realize, okay, this is number five. Okay. Now, let's say if this were to be some prize, social prizing schemes, right? Typically, what happens is when they're doing these draws, the number of times your name appears, the more of a winner you are. Okay, so if it's a draw where they're selecting five winners, what that simply means is if we're 10 people or we have 500 people that participated in that draw or in that raffle, maybe depending on the number of times that you texted to the program, right? If they run the draw and your name, person number five, your name or your number appears five times, okay, and five is the highest number of times that has been recorded in the entire raffle for the day, that it means person number five is the winner, okay? So number one, then followed by the second place. The second place may be the person who has the whose number of times follows the winner. Okay, so let's say for person number five, let me just do some writings here. So let's say for individual number five, um, individual number 10, individual number 21. Okay, let's say individual number six, and then individual number 13. All right. So let's say these are the high winners. So for individual number five, maybe for example, they texted to the show 51 times. Okay. For individual number text at for 10, they texted to the show, let's say 49 times. For the third place, individual number 21, they texted to the show, let's say 47 times. For individual number six, they texted to the show 45 times. And then individual number 13 texted to the show, let's say 40 times. Okay, now think about it. These are the individuals, but there are 500 people. Okay, now when you're performing sampling with replacement, it simply means that each unit, it's possible for each unit to occur more than one time. All right, that's the lesson in there. So for sampling with replacement, that occurs when we perform a simple random sampling, and we know what a simple random sampling is, right? So simple random sampling with replacement occurs when we perform a simple random sampling where or in such a way that for every selection that is made, the units or the element is reintroduced or returned back to the population. Okay, that's the whole idea. Whereas on the other hand, for simple random sampling without replacement, okay, in this case, it is the simple random sampling which is performed in such a way that for every unit or for every element selected, the unit is isolated from the population. In other words, it is not put back into the population. Okay, so an example of simple random sampling without replacement will be the typical lottery draws that they conduct on the television. Okay, I think there are 90 numbers. Okay, so what normally happens, you realize that they spin the wheel. Okay, they shuffle. That's a way of shuffling the population of 90 balls. All right, so that when they call on a random person from the audience to come and pick, the person will not know that number 9 is lying here, number 20 is lying here, and then will strategically pick and end up skewing the results. Okay, here what they do is they do the simple random sampling. I mean, yes, the SRS, the simple random sampling, by spinning the wheel, okay, for some time. Then they would call one person who comes to hit a button, and then at the end of the day, they would the first person would pick. So let's say they pick number 2. But what happens when they pick number 2? They don't put it back into the wheel or the ball, the wheel of balls. No, they put it aside. Okay, and then they would spin again. They would spin again, and this time around, maybe number 18 will appear. All right, they would show it to the audience. They don't put 18 back into the population. They exclude it from the population. So they do this, I think every week they select as a 5 balls, right? Good. So by the time they are done, they have 5 balls that have been selected. And so the 5 balls become the sample, all right? And then they will be left with 90 minus 5 balls still in the population, meaning 85 balls will still be in the population. Okay, so those are the two types of simple random sampling. In academic literature, you would see that we have simple random sampling with replacement. It's normally written this way, SRSWR versus simple random sampling without replacement. All right. So we're still looking at types of sampling. We're looking at probabilistic sampling and non-probabilistic sampling. We're currently focusing on probabilistic sampling, and we've looked at one type so far. That one type of probabilistic sampling is simple random sampling. We've explained what that is, and we're looking at two subtypes of simple random sampling, which is simple random sampling with replacement, and then simple random sampling without replacement. All right. Now, let's look at the second type. Okay, so in here, there's a bit of, I wouldn't say math, but well, I mean, of course, math. But so I would switch over to the other side of the screen where I'll do a lot more demonstration. But let's just understand just the theoretical perspective of what systematic sampling is. First of all, when we say something is systematic, just the name alone tells you that there's a sense of organization in here, right? There's a sense of things not being done in a haphazard way. Okay, it follows a certain science. It's a science. There's a scientific approach that underlays the process. Okay, so that's exactly what systematic sampling is. So for systematic sampling, it's the type of non-probabilistic sampling, I mean, the type of probabilistic sampling method which involves the random identification of an initial starting point in the population followed by a defined count interval. All right. Systematic sampling, once again, is a type of probabilistic sampling scheme which involves the random identification of an initial starting point followed by selection based on a count interval. Okay. So when I illustrate how this works, I hope that it will make a lot more sense. So I think what I have here are words. Okay, but so let me switch back to the other side of the writing area, and then we'll look at exactly in a lot more detail what systematic sampling. In order for us to understand the principle of systematic sampling, there are some fundamental mathematical principles that you need to understand. All right. So I want to talk about intervals, okay, because I'll need that idea to explain systematic sampling. So let's just put a few things down. So let's say basic. All right. So in general, when we say an interval, okay, as you would expect, it's just a range of values. Okay, but there are different ways of defining the range of values, and you need to understand the math behind it and the notations behind it so that as we move ahead, whatever interval I use, you can refer back to this and then understand. So in the first case, we can say that giving two integers, let's call them A and B. All right. So mathematically, we can say that. So this is the preamble for all. Okay, this symbol is for all. Okay, it's like an inverted A. Okay, so for all, wait, let me, okay. So this symbol, this statement here means that given any two integers, okay, this simply means given any two integers. All right. Z is the set of integers, okay, in mathematical language. Okay, when you see Z, we mean integers. And you know what integers are, right? Positive and negative whole numbers. Okay, if I'm referring to just positive integers, I would say Z plus, okay? And Z plus would contain positive integers. You should know what positive integers are, right? And then if I want negative integers, I would say Z minus, which means negative integers. But when I say Z without any positive or negative at the top, this is essentially the same as the set of negative integers union the set of what positive integers. Because it's the negative integers and positive integers that gives you integers in general. Okay, so this thing here is an element of. Okay, so this statement means this inverted A means for all. Okay, and this thing that looks like E, okay, simply means it's an element of or a member of. All right. So in a nutshell, this statement simply means for or giving two integers or for any two integers, all right, number one, I can write A, B like this. Okay. Now, when I write two values and I put them in a curvy parenthesis, okay, this simply means that the range of values between A and B, okay, between A and B. So this means that I am interested in some X values, okay, such that A is less than X and X is less than B, okay? So, for example, let's take 2 and then 9, all right? 2, 9 means that I am interested in values between 2 and 9, okay? So this means that I'm interested in the range of values, let's call it X, and X, 2 is less than X, and X is also less than 9, okay? This becomes what? The set of values. What are the values? And here we're talking of integers. And you know, integers are discrete values, okay? They are discrete data points because they are finitely countable, okay? So the values between 2 and 9, we're talking about between. So between means that the endpoints A and B are not included, okay? So values between 2 and 9, this finally will become 3, 4, 5, 6, 7, 8. Okay. So when I write, let's say 2, 9 in parentheses, this is actually what I mean. I mean these particular values. Okay. This symbol is like an arrow, two parallel lines, and then one triangle at the end. Okay, like a sharp PSC triangle. This means it implies. Okay, it implies. And it implies means it means. Okay, yeah, so this is just math vocabulary. Okay, so this is the first interval. We call this the open interval. So number two, I could also have a closed interval. So this is also parenthesis, but I'm using block parenthesis. Okay, now what does this mean? This means that I am interested in values from A to B. Keep in mind, the first interval says between A and B. This one is from A to B, meaning that the endpoints A and B are actually included in the interval. All right. So what does this mean? This also means that we're interested in some range of values, let's call it X, such that A is less than X, X is less than B. However, because the endpoints can also be included, not only is A less than X and X is less than B, A can actually be also equal to. So we have A is less than or equal to, okay, X, and then X is also less than or equal to B. Okay, good. So example, let's use the same example, 2, 9, 2, 9. This will mean that what we're interested in the values that move from 2 to 9. So 2 is less than or equal to X, X is less than or equal to 9. Okay, this means that, or this implies that we have what? It actually starts from 2 because 2 and 9 are included. We're talking about values from 2 to 9. Okay, so 2, 3, 4, 5, 6, 7, 8, 9. All right, good. So number three, what do we have? We can have a hybrid version, okay, a hybrid. So what I mean by that is we can have an interval which is partly open and then partly closed. So let's look at an interval which is open. Okay, it's partly open on the left, but closed, okay, on the right. This would mean that we're interested in values coming after A up to B, all right? Because we know what this curvy looks like. We took it from here. All right. Whenever you see the curvy bracket, it means the endpoint is not included. But when you see the block, it means the endpoint is included. So this simply means that we're interested in values going past A, okay, immediately following A, up to and including B. All right. So this is also another inequality. A will be strictly less than X, and X will be less than or equal to B. All right. Now, example. For example, if I have, let's say 2 and then 9, okay, this will mean that I'm interested in values such that 2 is less than X, and then X is less than or equal to 9. This will mean that my final set of values is the set 2 is not included, okay, because we're open on 2. So we'll be starting from where? 3, 4, 5, 6, 7, 8, and then what? 9. All right. Good. Now let's look at the fourth and final type of interval. Then we'll get back to systematic sampling. So we can have the reverse, okay, closed on A, open on B. So this would mean that we have a set of values X such that A is less than or equal to X, okay, but then X is less than, strictly less than what? B. Okay, so for example, if we have 2 and then 9, this will mean that we're looking at range of values X such that 2 is less than or equal to X, and X is strictly less than 9, which translates to the sets 2, 3, 4, 5, 6, 7, and then 8. So these are the basic types of intervals that we may be encountering. So giving this analogy, now let me go back to walk you through the process of, undertaking a systematic sample. So let me put a few things down. So systematic sampling. Okay. So the first step is what we'll say. We'll say that given population size n, okay, and sample size small n. Evaluates or determine all right, determine the determine what we call the sample fraction. F. Okay. Such that, or let me rather say defined as sample fraction F given as so we compute the sample fraction F. So F is equal to small n over big N. Okay, now this is the first important lesson that you need to keep in mind. Throughout the remainder of this course, we will be denoting population size by big N, and we will be denoting sample size by small n. All right, so whenever we want to refer to a population size, we'll say big N, and when we want to refer to a sample size, we say what small n. So moving forward, with that explanation, when I write big N or small n somewhere, you should know what they are. Big N is the population size, and small n is the sample size. And it should be able to stick, right, for easy recall because big N is big. So it refers to the population size. It doesn't refer to the population, keep in mind. It refers to the size of the population. So big N is a number. And small n is also not referring to just a sample. It is referring to the sample size. So small n is also a number. Okay, so we simply find the proportion. All right. So we call this proportion the sample fraction, which is essentially the proportion of the population that the sample forms. Okay, now once we find the sample fraction, step two, the second thing that we do is evaluate evaluates evaluates G, okay, such that G is the reciprocation of F. Okay, so after we find F, we need to find another quantity that we call G. And G is simply a reciprocal of F. What does it mean? So let's say given as G is equal to, what does it mean to take the reciprocation, right? It becomes 1 over the quantity. Okay, so when I say G is the reciprocation or the reciprocal of F, it means that G is what? 1 over F. Okay, G is 1 over F. And if G is 1 over F, then in terms of small n and n, G is what? It becomes big N over small n. Now, I believe all of you can understand how we move from 1 over f to big N over small n. Okay, this is a very basic. This is very basic from elementary math. So I'm hoping that I don't have to walk you through how that comes about. You recall from basic school that the idea of reciprocal simply means that when you have a fraction and you take the reciprocal, the denominator becomes the numerator, and then the numerator becomes the denominator. All right. But for the purposes of just to ensure that I don't end up leaving anyone behind, we know that I don't know whether this is important to do, but let me just do a quick. So we know that if G is equal to 1 over F, all right, and what is F? F is small n over big N. So it means that I have 1 over small n over what? Big N. Okay. And this is the same as if I want to write this out using another operator, is the same as 1 divided by what? N over N. Okay, and you recall from basic school that this is equal to 1. If you want to, you can change the division to what multiplication, and then you flip the fraction. So 1 times what? Big N over small n. And this gives you big N over small n. Okay, so therefore, whenever we say G is referring to the population size over the sample size. But once you find F, whatever value it is, just simply do 1 over that value, and you should still be able to arrive at this. Okay, so that's step 2. Now, step 3. Step 3. This is what we will do. Apply simple random sampling. Okay, apply SRS to randomly select. Okay, apply SRS to randomly select a certain value, okay, to randomly select some value, let's call it H. Okay, apply SRS to randomly select some H, where H, you see, H is a random number, okay, so we're calling it H, but we're selecting H in such a way that H belongs to the interval 1, G. Okay, apply SRS to randomly select some H such that that H belongs to, okay, or is an element of, or is within the interval 1G. All right, step 4. Starting from, please desist from writing across the screen. All right, so starting from H. All right, now H is a number. Starting from H, count and selects every gth. Okay, so now G has become a position. When I say gth, for example, if G is 4, gth would simply means the fourth. Okay, all right, so we are positionalizing the value. So starting from H, count and select every gth. Let me write every other gth. Every other gth value. Successively till n is exhausted. All right. So we begin from H and then we count every gth other element or units successively, okay, continually. We do this all the way till we hit the sample size. I mean, we hit the population size, okay? Then number 5, the resulting collection, the resulting collection of every gth other units constitutes the desired or the required constitutes the systematic sample. So these are the 4 or 5 processes that you go through in order to undertake a systematic sample. The very first thing that you do is I mean, we have, before we embark on the sampling scheme, we have a big N already. We know our big N, we know our population size, and then we have a sense of a target, okay, a sample size that we're interested in. Okay, so we already know our small n and then our big N. So the first thing is we find the fraction, our small n over big N. Then once we find the f, okay, we compute another g, which is simply 1 over f, okay, and that becomes big N over small n. All right, then we create an interval involving 1 and g, okay, and from that interval, we apply simple random sampling to select a value. Let's call that value h, okay. So when we get the h value, then we go back into the population and then we start from h. Okay, using h as a point of beginning, we now begin to count, and then for every gth other value or element, we select them or we isolate them from the population till we exhaust the population size. Okay, so when you're done, the resultant selection, all right, the resultant selection becomes your the resultant selection becomes your final systematic sample. All right, so let's use an example to see if we can understand exactly how this works. So illustration. Let's suppose that, let's take a very simplistic illustration. Let's assume that our population size is 100. And then out of the 100, we're interested in 10. Okay, so our sample size is what? 10. Now we want to perform systematic sampling. Okay, so the first step is let's find the sample fraction. We don't even need to write sample fraction. We can just simply write F. And F is what? N over N, which is 10 over 100, which is 1 over 10, which is what? 0.1. Okay, so our sample fraction is 0.1. 2. Reciprocated sample fraction. Okay, we call that the G. Okay, G is 1 over F, which is what? 1 over 0.1, which is what? 10. Three. Okay, applying SRS applying SRS. Okay, choose H. We don't know what H is because it's random. Okay, however, we define some boundary values of H. We know that H would be what? A value moving from 1 all the way to what? G. And G here is what? 10. All right. Now we know what these values are. The values of H the possible values of H will be what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because the endpoints are inclusive. Okay. Now here, because it's a random selection, somebody may end up selecting number 1. Somebody may end up selecting number 10. Somebody may end up selecting number 5, because we're doing the selection by simple random sampling. And you know what that means? We need to shuffle the population and then we make one selection. All right. So there are 10 possible selections that could come up. All right. However, for purposes of illustration, let's assume or suppose you're selected H. Suppose randomly selected H is equal to 5. Okay, this is an assumption. Suppose that the randomly selected H is 5. So then number 4, we say that starting from number 5 in the population, okay, let's go back to look at the steps. We've come all the way up to number 3. All right, so we're saying that starting from H, count and select every other GS or every GS other value, okay, successively till N is exhausted. All right. So what does it mean? So let's go back. So here, starting in the population, I mean, we go back to the population of 100 people, okay, supposing that everybody has been given numbers. And then I'll start from population member 5, okay? So from 5, I will count the gth other person. Here, the gth other person means the 10th other person. So I'm starting from number 5, okay? So watch this. So from 5, the 10th person after number 5 is what? The 15th person, okay? So number 15, the 15th person. So 15 is my first choice, okay? Then from 15, I'll count the 10th other person. So that's the same as the gth other person. So after the 15th person, who comes next? 25. After the 25th person, who comes next? The 35th. After the 35th, who comes first? 45th. After 45th, we have 55th. After 55th, we have what? 65th. That's the 10th other person. After this, we have what? The 75th person. After this, we have the 85th. And then after this, we have the 95th. All right. Yeah, I mean, we're starting from number 5. So, I mean, obviously, this guy is part. Okay. So, once again, the random value that we selected was H. That's why if you go back to the definition, I said that systematic sampling involves the random identification of a starting point. Okay. So, this is the random identification of the starting point. We randomly decided that the starting point is 5. Okay, so number 5 is where the selection takes place. So we start number 5. Okay, then who is the gth other person after number 5? That's the 10th other person after number 5 is 15th. The 10th other person after 15 is 25, 35, and so on and so forth. You realize that we've gone all the way to exhausting the population because after here, when I take the 10th person after number 5, it will be the 105th person. But 105 is after 100. And at this point, we've exhausted the population. The 105th person is not in the population, right? Because our population is up to 100. So let's count and see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Exactly. So you realize we end up getting a sample containing 10 people. So the final systematic sample is the members 5, 15, 25, 35, 45, 55, 65, 75, 85, 95. So meaning that if I am selecting 10 students, students with these numbers, assuming we've given all of you numbers, okay, somebody's number 1, number 2, number 3, all the way to number 100. It means that my final choice of 10 students would be number 5, number 15, number 25, number 35, 45, 55, 65, and so on and so forth. But the beautiful thing in this approach is it doesn't matter the number that you choose because it's random, it would still work. But we'll end up getting different samples, which is fine because, again, this is a probabilistic sampling approach. It's probabilistic, keep in mind. All right, good. So let's try another example. Let's say that instead of selecting, let's say number 5, what should we select? That we select number 2. So let me do this. So let me draw Okay. Now, suppose H is 2. All right. Then we would have the following. It means that what? Again, your H becomes your starting point. Okay. And from H, we count the gth other person. So here, we are starting from H is equal to 2. Okay. Now, who is the gth other member after 2? In other words, who is the 10th member after 2? It's 12, right? All right. The 10th member after the second person is number 12. The 10th member after number 12 is what? 22. The 10th member after number 22 is what? 32, 42, 52, 62, 72, 82, and then 92. Okay. So that's our systematic sample will now be equal to 2, 12. So it means if I'm selecting the final set of students that I'll be selecting will be the second person, the 12th person, the 22nd person, the 32nd person, the 42nd person, the 52nd person, the 62nd person, the 72nd person, the 82nd person, the 92nd person. All right. Yeah. And if we count, we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the next person after the 92nd person will be the 102 or the 102nd person. And the 102nd person doesn't exist because our population ends at 100, meaning that we've exhausted the population. Okay. So this is how you go about it. I'll encourage all of you to experiment with other values. In fact, you can define your own big N and then your own small n and go through the process and try and select different H's. At the end of the day, your answers should still be very scientific. Okay, so you realize that here it's very systematic in the way we select the values. All right. So this approach is very useful when we want to ensure diversity. Okay, when the population is very widespread and we want to ensure that we include as many demographics as much as possible. All right, good. Now let's look at the third approach, cluster sampling. For cluster sampling, right, this is it. There are a couple of things I would say which are not necessarily on the slide. Okay, so we're saying that here the population is divided into clusters, each representative of the population. Okay, a simple random sample of clusters is selected. All items in the selected clusters can be used, etc. When we say a cluster of something, we're referring to a group of entities or a grouping or a classification which has some similarities. Okay, they share some similarities. All right, there is similarity. So if we say a cluster of schools, they may be situated in different localities, but then they have some common characteristics. Okay. So in general, when we talk about a cluster of something, right, statistically or quantitatively, there are two things you need to keep in mind. The idea of homogeneity. Okay, and then what? Hetero. Okay, so we all know when something is homo versus hetero. Okay, homo simply means identical or sameness. Okay, or at the very least similar. All right, hetero means different or distinct or unique. Okay, so in general, we'll say that a cluster. Okay, so refers to refers to a cluster refers to a grouping. A cluster refers to a grouping of units okay, which are internally homogeneous and externally or mutually heterogeneous. So let me give you an example. If we take the university, for example, okay, the university has 5 faculties. So we can think of the faculties as clusters. Why? Because if you look at faculty of business, for example, there's marketing, there is supply chain management, there is secretaryship and management, there is name it, several. Okay, there's accounting and finance, there's so many other business related programs. Now, you realize that whether you're reading marketing, supply chain management, and so on and so forth, your programs are still all very much related. Okay, all of your programs are still very much related. So you belong to a cluster. So internally, that's why you're grouped in the faculty of business. Okay, good. So, but if we come to, let's say, faculty of applied sciences, okay, faculty of applied sciences is made up of the Department of Mathematics and Statistics, the Department of Medical Laboratory Technology, the Department of Science Laboratory Technology, and then the Department of Computer Science. Okay, you realize that although these programs might have their distinctions, but they're all very much related. Okay, they're all very much related. So they're grouped together. All right. But here's the catch. When you go into the faculty of business, they're all the same people. They have the same academic background. They probably read the same programs, okay, or very similar programs. Whereas if you come to the Faculty of Applied Sciences too, they have the same background. They probably read the same programs or relatively similar programs. However, when you move outside of the faculties and you compare faculty to faculty, you realize they are different people. So if you take Faculty of Business versus Faculty of Applied Sciences, the average student in Faculty of Business would be different from the average student in the Faculty of Applied Sciences, which would also be different from the average student in the Faculty of Applied Arts, which will also be different from the average student in the Faculty of Engineering, and so on and so forth. Okay, so that's what I mean by a cluster refers to a grouping of units which are internally homogeneous. For internally, they're all the same people or they're very similar. But if you move outside and you cross compare them, you realize they are different people. Okay, so that's what we mean by a cluster. So a cluster sampling is basically sampling in such a way that we make recourse to this issue of homogeneity and then heterogeneity. Okay, but there are a couple of steps that we need to go through in order to carry out a cluster sampling. So number one, first of all, partition into clusters. So now you know what clusters are. In other words, divide the population into groupings which are internally homogeneous and then externally heterogeneous. Okay, number two, is apply SRS to select a reduced number of clusters. Number three, within each cluster. So within each selected cluster, apply a apply any alternative probabilistic sampling method consistently. And then number four, the resulting collection of units constitutes the cluster sample. What would happen under cluster sampling is when you go to the population, you partition the population into clusters, and you know what clusters are. They are internally or within themselves, they are similar, they are identical, but outside, once you move outside, they are different. So you need to identify such groupings. Now, the key thing here is it doesn't mean you walk into any population and then you begin to do the partitioning, because it will cost you a lot of money and time, if at all you can trace the population. The best practice is normally you go to the population and then identify what we call natural clusters. Okay, there are natural clusters. So for example, if you're coming to ATU, all right, to come and conduct a study, or to perform some research and you want to do this by cluster sampling, it would cost you a ton of money to want to demarcate the student into some partition. No, there are natural clusters that are waiting for you. And one of the most natural clusters are the faculties, okay? Because every student within the institution, every student and every member of staff, okay, would belong to one faculty, okay? So the the faculties are internally homogeneous, but externally heterogeneous, all right? Another, let's say, another type of natural cluster could be regions, okay? Each of the 25,000 plus students in ATU would come from at least one region in Ghana, if only they're Ghanaians. Okay, I'm not talking about the international students, but Ghanaians, all right? So Northern region, Central region, Eastern region, Ashanti region, Volta region, Ochi region, and so on and so forth. All right. At the end of the day, you realize that they're internally homogeneous, but externally they are heterogeneous. Okay. Because the language that is spoken in, let's say, the central region will be different from the language that's spoken in the Savannah region. Okay, so they're separate. So, I mean, another natural cluster could even be gender, right? Every person in the institution would either be a male or a female. And males are internally homogeneous, right? If you look at the male bracket, most males have very, very similar characteristics. Okay. And then most females too would have very similar characteristics. Okay. But if you move outside of male-female domain, males are different from males. Okay. Although we're divinely the same in terms of in the scriptural sense, okay, we're divinely the same, but we are statistically different. Okay, so statistically, males and females are different, but before the Most High God, we're all the same. All right. Okay. So you do the partitioning, then you get a lot of partitions. What you will do is you would apply the simple random sampling frame to identify or to shortlists from the clusters. So you'll get a reduced number of clusters. Then now you go into each of the clusters and then you apply an alternative probabilistic sampling method. Now the key thing here is consistently. So for example, if you are in cluster A or cluster B, when I say consistently, I mean when you're using an alternative probabilistic sampling scheme, use the same thing across board. All right. So if you're using maybe simple random sampling for let's say Faculty of Applied Sciences, when you go to Faculty of Applied Arts, go and use the same simple random sampling there. Don't go and use simple random sampling in one cluster and then you're using systematic sampling in another cluster. Okay. And here, when I say alternative probabilistic sampling methods, so far we've done three. The cluster is a third part. There's a fourth part that we need to look at. So when I say alternative probabilistic sampling methods, I actually mean simple random sampling, systematic sampling, and stratified sampling or stratification, which is the next thing that we will do. Okay, so this is how you conduct cluster sampling. So let's look at stratified sampling. That would also involve a bit of computation, but we should be able to get over that. So this is the fourth probabilistic sampling method that we're studying. Stratified stratified sampling. Stratified sampling, right? This is a type of probabilistic sampling method or technique which involves the use of proportions to obtain sample sizes for strata in a population. All right, a type of probabilistic sampling method which involves the use of proportions to obtain sample sizes for strata in a population. So the key thing about stratified sampling is that the key word here is stratum. Now, when you think about stratum, I want you to think about a homogeneous grouping. Okay, so that's why we did cluster initially. So when I say people that belong to the low income stratum, okay, they have similar characteristics. Okay, so the low income stratum, we have high income stratum, we have mid income stratum, and so on and so forth. All right, so essentially they're also clusters, but they are more specialized cluster, and we call them stratum. If it's singular, we call it stratum. If it's plural, we call it strata. It's like saying stratums, but I mean the correct thing to say is strata. Okay. Now, in general, the respective so does strata mean group? So that's just what I'm saying. Not just any group, but a grouping that shares similar characteristics. That's the point. So a strata is a grouping with homogeneous units. That's it. Okay. Not just any grouping. A grouping in which the units are homogeneous. In other words, they share similar characteristics or they're identical. So in general, the respective sample, the respective strata stratum sample sizes. Okay, we call that N STR. We know what N is. N is what sample size. Small n is sample size. So as a subscript, okay, not underscore, as a subscript, I write N STR with the STR below. This statement means stratum sample size. Okay, so in general, the respective stratum sample size is NSTR. Okay, are obtained proportionately as n str is equal to big N str over n times n. Okay, so this becomes n str multiplying n all over n. Now, let me illustrate how to perform a stratified sample or sampling with an example. So let's just create an example. So let's say that example, the government of Ghana, okay, the GOG, okay, is implementing a tertiary financial aid scheme. The government of Ghana, the GOG, is implementing a tertiary financial aid scheme to support the educational financing of 1,000 university students across five constituencies. As follows. Okay, so the data is as follows. So profiled as follows. All right, so we have 5 constituencies, so let me create a data set. Let's say constituency, and then we have what the counts. The count is the number of people in the constituency. So let's say that we have what Ayawaso. We have Ododo Dio. We have La Dade. Is it Kotopong or something? So let me call it LDK. Okay, and then we also have Lejo Kuku. So L, D, Z. And then we have, let's say, Ablekuma, A, B, K. Now, just for purposes of illustration, let's assume that Ayawaso is made up of 5,000 people. ODD is made up of 4,000 people. LDK, 3,000 people. Lejo, 2,000 people. Ablekuma, 1,000 people. Now here you see that the population is decreasing. It's just a coincidence. All right. It doesn't have to be like it doesn't matter what the various constituency populations are. This approach would still work, right? It's just because I'm illustrating. So the example ended up giving me these numbers. So the question that we are trying to answer in this regard is this, right? How do you see the government can only spend on where? 1,000 university students. The government has scarce resources. It cannot take care of every university student in the country. Okay, so the government is saying that for 2024, I can only fund 1,000 students. But I want to focus on just 5 constituencies for this year. Next year, we'll see what happens. Okay, the question that the government would want to find out or would want to answer is how many people can I support in Ayawaso? How many people can I support in ODD? How many people can I support in Lejo? How many people can I support in Ladade? And how many people can I support in Ablekuma? In such a way that I would fairly, the key word is fairly, okay, that I would fairly or equitably distribute the 1,000 opportunities across board. You see, if the government is fair, and you don't even end up getting some of the financial aid, you would still be happy because you realize, oh, the distribution was made very fairly. But in the case where there is corruption and somebody hijacks the scholarship secretariat and it's only family members who are getting scholarships and things like that, it becomes a bit of a problem. All right. Yeah. So this is it. Now, and by the way, just as a caveat, this example and this point that I just made is not political, okay? In the current government and in previous governments, in the previous government as well, there were instances of corruption across the scholarship secretariat. Okay, so corruption in these regards, with regards to financial aid schemes for higher education, is not simply limited to the current government, but also the previous government. Okay, so in that regard, corruption has been identified across board. So it's not a peculiarity that I'm citing. It's a general issue facing our country, regardless of government or party. All right. Okay. So the question is, how do we do this? Supposing that you were maybe in the next few years, you end up being the secretary to the president. Okay, you are the executive secretary to the president. All right. What you could do to help the president is instead of just telling the MPs to bring 1,000 people where somebody would hijack and things like that, you can be a bit more specific and you can apply stratified sampling to actually create a quota, okay, for all the MPs. So you don't tell the MPs, oh, we need 1,000 people, so bring people, right? Somebody may end up bringing 800 people, and those who actually have students in their constituencies who need help may end up getting fewer slots. So the question is, or if you were to be the executive secretary to the government, what you will do is you would now use stratified sampling or stratification to create a quota system so that you would say that, okay, Ayawaso MP, I want X number of people. ODD, I want X number of people. ABK, I want X number of people, so that it makes it more specific. Okay, so of course, in that regard, it would not eliminate corruption totally, but it would ensure that, there's a lot more reasonability in the number of people that you're bringing in. All right. So this is how we go about it. We have constituency, and then we have what counts. And then we also have, so we can create another column, and then let's call it the NSTR. Let me write the full name and then we'll put it in parentheses. So this is the stratum sample size. So okay. So the question is, how many people should we take from Iowa? So ODD, LADD, and so on and so forth. We apply this thing here. Okay. So the first thing is we need to take the total population across board. What is the total population? 15,000. Because this is the total population, we say N is equal to what? 15,000. All right. So think about it. Ayawaso is a stratum. ODD is a stratum. Latter day is a stratum. Ledger is a stratum. Obliqua is also what is a stratum. Okay. So overall, we have 15,000 people. So we have our big N here. Now we need to find this value, the stratum population sizes. Okay. So the stratum population for Ayawaso is what? 5,000. The stratum population for ODD is 4,000 and so on and so forth. So in order to obtain the NSTR for Ayawaso, it would become what? The big NSTR, so 5,000 over big N, 15,000 times the target sample, N, okay, N. Okay, you can be computing this for me. So this is 5,000 over 15,000. That's 1 over 3. 1/3 of 1,000 is 333.33. All right. Then we come to number 2. Similarly, we have what? 4,000 over 15,000 times 1,000. Okay. That would give you something. You can compute and give me the values. Then thirdly, we have what? 3,000 over 15,000 times 1,000. That 3,000 over 15,000 is 1/5. 1/5 of 1,000 is what? 200. Then we have what? Ledger. The stratum sample size will be 2,000 over 1,000 times 1,000. Okay, and then finally we have 1,000 over 15,000 times 1,000. Can anyone compute these and tell us? I don't know if you've done this. Okay, so the ODD, I think, yeah, okay, so we have what? 266.66. Because it's to 2 decimal places, it becomes 0.67. All right. Then 2,000 on 15,000 times 1,000 becomes 133.33. And then I think the last one will be 67. But you can verify for me. And then we have 66.67. Okay. Yeah. So, Madam, this is Ivy Idri. Thank you very much. Good. So there you have it. So meaning that you will tell the various MPs to bring these number of particular people. Okay, so Ayawa, so bring me 333 names. Okay, vetted names. ODD, bring me 267 names, and so on and so forth. Right now, the thing is, when you do this correctly, okay, I want you to sum up, the values and tell me what you have. So 333.33 plus 266.67, and so on and so forth. When we add all of these, okay, we're going to get exactly 1,000. Okay, this means that this process is indeed very scientific and very equitable. Okay. Yeah, Helen is also confirming. So at the end of the day, we'll get 1,000 people, which is exactly the number of opportunities available. Okay. Now, here's the thing. Typically, depending on the context, we may have to modify these values a bit. Because these are human beings, okay, these are human beings, we oftentimes will be asked to round off to the nearest whole number. It looks like it's just the ladies who are following the proceedings. I don't know if there are any males still in the meeting, but well, anyway, the ladies seem to be dominating the discussions. Okay, so because these are real human beings, human beings, we'll try to convert to the nearest whole number. So in the first place, it would be 333 people. Okay, we can discard the 0.33. In the second place, the ODD, it would end up being 267 if we're rounding off to the nearest whole number. Okay, you remember how to round off to the nearest whole number, two decimal places, right? I mean, these things back in the day. As for 200, it's constant. Then 133.33, if we're running off to the nearest whole number, it will be 133. And then for Ablekuma, if we're rounding off to the nearest whole number, it would be 67. All right, good. And even with the whole numbers, when you add them, you should still get a number very close to 1,000, if not exactly 1,000. Okay, so this is what stratification is about. It helps us to obtain, you see, the previous sampling methods that we've looked at, they all help us to obtain the sample constitution for, in just a single instance. But for stratified sampling, it helps us to obtain the sample for, different groupings or clusters, or for different stratum or strata. Okay. So the thing is, here you've identified the 333 people, 266 people, and so on and so forth. Then if you want to actually perform the sample, if you actually want to select the number of people, then you will go into these various populations. You'll go to Ayawaso and then go and apply SRS, cluster, or systematic, okay, to be able to get 333 people. All right. Or you'll go to Odiodio and go into their population and then go and apply SRS, systematic, or cluster sampling to arrive at 266 or 267 people, and so on and so forth. But here we are only interested in the sample sizes. Okay, the sample sizes. So I think with this, if you're given some other problem on stratified sampling, you should be able to do it well. The key thing is about proportions. Okay, proportions. So you take the size of each stratum divided by the the total of all the stratums or the total of all the strata, okay, times the intended target sample. All right. And when you do that, you've performed stratified sampling. Good. Now let's move to non-probabilistic sampling. So this is just a quick comparison. All right. Simple random sampling and systematic sample, they're simple to use. They may not be good representation for population with underlying characteristics. Some stratified sample ensures representation of individuals across the entirety of the population. All right. I mean, because we're making use of proportions. Cluster sampling is more cost effective. It's less efficient. You need a larger sample to acquire same level of precision. Why? Because you realize that for cluster sampling, we need to first of all apply SRS to shortlist the clusters. Then we'll go inside of the clusters to go and do another sampling. So it means you would end up getting a very limited number of units at the end of the day because it's more like a sample within a sample. So you need a large sample to start with so that when you do the reduction, you still would have something left. Okay, so non-probabilistic sampling, as you recall, we said that for non-probabilistic sampling, it doesn't ensure that every member of the population has an equal likelihood of being selected, right? So that's just about it. They were only interested in obtaining a defined number of units. That's all. We don't really pay much attention to the signs involved. All right. So the first type of non-probability sampling or the first type of non-probabilistic sampling is what we call convenience sampling. Convenience sampling. Okay, convenience sampling, or what we also call accidental sampling. Okay, so here subjects are selected just because they are easiest to recruit for the study. A population is selected because it is readily available and convenient. It may be through meeting the person or through technological means such as the internet or through phone. So let me quickly explain this. Convenience sampling is basically sampling. Convenience sampling is a non-probabilistic sampling method which involves sampling based on proximity to the population. So, for example, let's say that you are the branch manager for a telecommunications company, all right? Or you're the corporate secretary for a telecommunications company or the corporate manager and you're coming up with some package for students, all right? And say you are interested in experimenting the package with 500 students. What would you do? You would not, if you wouldn't go to a place like, let's say, Medina Market, okay, or Malata Market or some other place, right? Your best bet will be to go to the universities because that's where the kind of people that you're looking for will be. Of course, Medina Market, you would still find young people, school-going people, right? Educated people, youth in general. But you are more likely to find the caliber of youth, okay, who will benefit from this product more in the universities, maybe ATU or UG or UPSA or some other institution. All right, good. So the key thing here is I want 500 students, to kind of experiment with a product. And I want young people. So what I'll do is I can come and station some some of the staff or some of the workers. Maybe they'll be dressed in the corporate brand. They'll be dressed in the what's it called? The t-shirt or whatever. Their branding clothing. And maybe they're having flyers. Okay, they're publicizing it by using flyers. Okay, so if they're just standing at the front gate or the back gate of ATU, they would simply say that okay, anybody who comes out will just give him or her a flyer. So it doesn't matter whether you are a Faculty of Applied Arts student, applied science student, engineering student, built environment student, it doesn't matter. We are just interested in giving samples or giving free versions of our products to 500 people. You understand? Or 500 students. So here you are sampling based on proximity to the population. Okay, because ATU is, let's say, in central Accra, and maybe the company is also in Accra. Okay, let's take a company like, let's say, Tigo. Tigo has its head office just on the north of the Barnes Road, okay, of ATU, very, very, just a few kilometers away. So Tigo, for example, can just say, oh, ATU is just around the corner, all right, in the central hub of Accra. All right, so let's just go there, station some of our people, and just give freebies to 500 students that come in and go out. Okay, so it's convenience sampling because they are sampling based on proximity, okay, or closeness to the population. The population here is ATU. All right, okay. Now let's look at the second one, quota sampling. So quota sampling is selection with controls, ensuring that specified numbers, or what we call quotas, are obtained from each specified population subgroup. No randomization of unit selection with the subgroups, and no population list is used. So you realize that for even if you look at the accidental or the convenience sampling frame, there was no randomization, right? It could happen that all the 500 people are even coming from the same department or the same faculty, but we really don't care. Okay, we're only interested in just engaging with people who are in proximity to us. That's all. All right. Okay. So with quota sampling, what happens is we have a predefined set of numbers. Okay. So let's say we want 500 people. All right. We have 500 people. So here there are a few, let's say, controls. We can say that, okay, so with the 500 people, I want 250 males and 250 females. That's what we mean by specified numbers are obtained from each specified population subgroup. Okay, so not only do I want 500 students, I want 250 males and 250 females. So when you segregate them into that regard, then it means that you are having that grouping, subgrouping, or you're doing a quota sampling. So it means that you have 250 as a quota for males and then 250 as a quota for females. All right, and so on and so forth. Let's say if it's a religious, for example, let's say elections are coming, and then NCC, National Center for Civic Education, right? They want to host a conference, okay, and the conference is intended to bridge unity across even different religious or different faith persuasions. Okay, if they want to do this by quota sampling, they could say that okay, we are organizing the meeting at Movenpick Ambassadorial Hotel in their conference room. It houses 500 people, so we need 250, let's say Christians, and then 250 Muslims. Okay, that would be quota sampling. So with the 250 people, they can also go to, let's say, the ATU mosque, for example, they can go and stand maybe a few meters apart. And then anybody they see going to the mosque or coming from the mosque, they would maybe give them an invitation or an invite or something of that sort. Okay, till they get 250 people. They can also go to the church unit or the Christian unit on campus, and anybody who's going there or coming out. So in that regard, they're able to get 250 Christians, 250 Muslims, and they get 500 people. That's quota sampling. Okay. Third, purposive sampling. Okay, purposive sampling, what we also call judgmental sampling. Purposive sampling targets a particular group of people when the desired population for the study is rare, okay, or difficult to locate and recruit for a study. It's based on selection of units on personal judgment rather than randomization. It's used in studies on for very small numbers of areas or sites. Okay, now just to summarily explain what is going on here. You see, we call it purposive sampling. So it is purpose driven. It is purpose driven. So That's the key thing. So anything that's purpose driven is also based on judgments. Okay. So there's some judgments thing going on here. So we are deciding. So I'll give you an example of purposive sampling. Supposing, supposing that the government wants to conduct a study. Okay, the government wants to conduct a study to identify, to take, let's say, opinions or constructive opinions from Ghanaians based on, I mean, constructive opinions on the free senior high school policy. Okay, free senior high school policy. Now, if they are doing this by a questionnaire, okay, let's say a Google Forms or Google Sheets, or even if it's, yes, a Google Sheet and they are floating it on social media. So anybody who stumbles on it can just participate in the study. The government can do something like this purposively or judgmentally. What that would mean is, you see, purposive sampling or judgmental sampling is the type of non-probabilistic sampling where where units are included based on pre predefined characteristics. Okay, so there's a non-probabilistic sampling scheme where units are included, okay, in the sample based on predefined characteristics. Quickly, this is what I mean. So I'm interested in performing a study on free senior high school. Okay, so I can say question number one. Question number one, in what year did you complete senior high school? And then I would list a number of possibilities. Okay, I'll list a number of possibilities. Now, this is the thing. Once you choose, let's say, 2000 and let's say 2012, the next question that would come, it would not be a question, it would just be a statement. It'll just say, thank you for participating, or thank you for availing yourself for the study, goodbye, or something like that. Okay, we just close the study on you. Why? Because just by entering 2012 or 2013, the algorithm at the background, we can tell that you are not a beneficiary of free senior high school yourself. So your opinions don't really matter. Everything else that you're going to say in this survey will be purely based on what you have heard or what's maybe a family member's, viewpoint is. But we actually need people who have gone through the free SHS system to give us feedback. Okay, so once you choose 2012 or 2013 or 2005, the survey will be closed on you and you'll not be able to continue. So when we do that, we are sampling purposively because it is purpose driven. Okay, you completing school in 2012 doesn't serve our purpose. Okay, free senior high school I think came into the picture sometime, is it 2015 or 2016 or 2017? I'm not sure. But I think most of you are beneficiaries of free senior high school. Okay. So technically we're interested in people who completed school maybe 2017, 2018, 2019 through till now. Okay. Uh-huh. So if you choose any year group within this range, then the following question would come. Okay, maybe what are your what's your opinion on the feeding aspect of the, whatever, the free SHS? Second, next question, what is your opinion on the infrastructural aspect of the free SHS policy, and so on and so forth? Because you qualify, okay, judgmentally, you serve our purpose. All right. So that's purposive sampling. This is it where units are included, units from the population are included in the sample based on predefined characteristics. So if you meet our characteristics, you are included. If you don't meet our characteristics, you are excluded from the study. Okay, finally, I'm done. Finally, We call it snowball sampling. Normally, when snow falls, okay, and then you're standing at one end, and then there's somebody else standing at an alley, and you pick a very small ball of snow. When you throw it along the ground, as it goes, it picks up snow particles, and by the time it gets to the other person down the alley, it becomes bigger than it started. Okay, that's what we mean by snowballing. All right. So we're saying that snowballing or snowball sampling is a technique where is a non-probabilistic technique, okay, where existing study subjects are used to recruit more subjects into the sample. Okay, so current participants refer or identify other possible subjects. It's often used when members of a particular population are difficult to find. So here, there's a type of non-probabilistic sampling scheme where the study investigator uses existing units to obtain more units to be included in the sample. All right. So, for example, so it's more like a referral system. All right. When I participate in the study, I can refer another person. The other person can also make a referral, also make another referral, and by the time that I'm done, I have the sample size that I'm looking for. Okay, so we're saying that this is normally used when members of a particular population are rare to find or difficult to find. I'll give you an example. Let's say individuals living with some illnesses. Okay, so for example, people living with, HIV/AIDS, for example. If you're performing a study on people living with HIV/AIDS, I don't think you don't expect that you just announce the study people living with would need 500 people living with HIV/AIDS, and you expect that somebody just shows up, hooray, we've come for the study, here we are, interview us. No, because of the stigma attached to these kinds of conditions. So you don't expect that people will just show up and tell you that they have this. Meanwhile, these people, they are people that live with us. They are our neighbors, you know, they are people just like us, right? But it's not written on their faces or shown on their foreheads. Okay. In fact, by mentioning this, I also want to encourage all of you as students to take very good care of yourselves. Okay, there's a lot of promiscuity in our institutions these days, and young people like you, okay, early 20s, mid 20s, and so on and so forth, even younger, are contracting all manner of illnesses that could have been avoided. And this ends up, you know, being a big dent, a big blot in their lives. Okay, these things it's not reversible. Okay, when it happens, you would hope that I wish, but it's too late. All right, so please, um, I know exactly what I'm saying. All right. I just take good care of yourselves. You came to school for a particular reason. You can have friends, you can have fun and things like that. But let there be restrictions on the extent that you go. Don't get yourself involved in promiscuity, okay, and lifestyles that will not inure to your benefit or I mean, will not inure well for your future. Okay. Don't think that you're playing smart. And don't think that, indulging in premature pleasure will take you anywhere. Okay, there would always be a day of reckoning. Okay, so please just be very conscious, very sober individuals. There's time for everything. Okay, so that's just by the way, just a quick admonition. All right, so now let's come back to this example. So in this regard, maybe you know just one person. Okay, you go to maybe a particular hospital, and then they will point you to one person who is a victim of that disease or that illness. Now, after you engage with a person and the person is done, the person understands the study. Maybe it's a study on the use of antiretroviral drugs. Okay, you know what antiretroviral drugs are. It's normally meant for people living with the condition. Okay, so the person realizes that, okay, wow, this study can actually benefit other people who are living with a condition. So the person will tell you that, okay, you know what? There is this group that the person belongs to. Maybe they meet every Saturday, maybe online or in person. I can recommend you to maybe other people he knows because the person he himself is living with the condition. It's very likely that he also knows other people who are living with the condition, right? And those other people would also know other people who are living with the condition, and so on and so forth. So here you realize that the population is very rare. You can't easily find such people on the streets. Okay, so from one person, you get two people. From two people, you get four people. From four people, you get six people. The sixth person leads you to the 10th person. And by the time you do this for over a month, you've gotten your 500 people. When you do that, we say you are snowballing. Okay, because you started with small and now it becomes a big, okay, a big ball. So it's snowing. All right, good. So, ladies and gentlemen, this brings us to the curtains draw of our conversation on sampling. Uh, just to summarize with this is what we've done today. All right, we've looked at types of sampling. We've looked at probabilistic sampling and then non-probabilistic sampling. We said that probabilistic sampling involves, where each member of the population has a known non-zero likelihood of being selected. In other words, they all have an equal opportunity of being selected. Under non-probability sampling, not every member of the population has an equal chance of being selected. Okay. Under probabilistic sampling, we have simple random sampling, which can be with replacement or without replacement. Systematic sampling, we randomly identify an initial starting point, followed by successive selection based on a defined interval count. Okay, so every gth other element we select, and you know the process. Cluster sampling, we talk about homogeneity and heterogeneity. Okay, and then stratified sampling, we sample based on proportions. So non-probability sampling, we have what? Convenience sampling, which is sampling based on proximity to the population. Purposive sampling or judgmental sampling, this is sampling based on based this is sampling where units are included based on they satisfy some predefined criteria. All right. So when you're satisfying the criteria, you're included in the study. If you don't satisfy the criteria, you're not included in the study, you're excluded. Okay. Quota sampling is an extension of you know convenience or purposive sampling, where we divide the population into subgroupings and then we select a non-probabilistic number of people or units from each of the subgroups. Okay, and non-random selection from each of the subgroups. And then for snowballing, where you use existing units in the study, okay, to recruit or to obtain further units for your sample. Thank you very much for your time. I'm grateful for dishing out your Saturday evening. So as the Lord wills, we will meet in the coming week in person. All right. Okay. Thank you very much. Have a good night.